The role of dissolution tests. Dissolution tests are used for many purposes in the pharmaceutical industry, in the development of new products for quality control and to assist with the determination of bioequivalence. Recent regulatory developments such as biopharmaceutics classification scheme have highlighted the importance of dissolution in the regulation of post-approval changes and introduced the possibility of substituting dissolution tests for clinical studies in some cases. Therefore, there is a need to develop dissolution tests that better predict the in vivo performance of drug products. This could be achieved if the conditions of the gastrointestinal tract were successfully reconstructed in vivo. Numerous factors need to be considered if dissolution tests are to be considered biorelevant. They are the composition, hydrodynamics, which are fluid flow patterns, and volume of the contents in the gastrointestinal tract. There are several physicochemical and physiologic factors that control the dissolution of drug products in humans and need to be considered when designing dissolution tests. They are the composition, mixing patterns, and volume of the contents in the gastrointestinal tract. The gastrointestinal tract is an organ with a multitude of functions and drug products. Foods and nutrients can remain in the GI tract for up to 24 to 30 hours if they are not completely absorbed. The conditions of the GI tract vary with the location of the segment of intestine. The factors that control the dissolution of the drugs in the GI tract can be linked to Noyes-Whitney equation. Therefore, the effective surface area has a significant effect on dissolution. To manipulate the effective surface area of a drug, a formulator may attempt to reduce the particle size to increase wettability. In the intestine, however, there are natural surface tension reducing agents that promote drug dissolution. Most of these natural surfactants are found in the secretions that come from the stomach and bile. If one were to design a biorelevant dissolution test for drugs with poor dissolution characteristics, it would be important to account for the natural surfactants located in the stomach and intestine. The maximum solubility of the drug in the intestine is influenced by many factors such as buffer capacity, pH, presence of food, and natural surfactants such as bile salts and lecithin. The presence of a meal in humans immediately raises the pH of the stomach from its normally acidic state, which is between pH 1.5 to 3, to pH 5.5 to 7. This could dramatically affect the solubility of drugs, which in turn can affect the oral bioavailability. The diffusivity of the drug, or its natural ability to diffuse through the intestinal contents, will be a function of the viscosity of the intestinal contents. Viscosity will depend on the level of natural secretions, which may vary in the fed and fasted states, and the presence of food. The boundary layer thickness around the dissolving particle will depend on how vigorous local mixing is. In other words, if motility or mixing is higher, then the stagnant layer surrounding the particle will be smaller. If mixing is reduced, then the stagnant layer becomes larger and may alter dissolution. For dissolution to proceed, there must be a driving force. The driving force is represented in Noyes-Whitney equation by the term Cs, which is the solubility, minus Xd divided by volume. If the difference between Cs and Xd divided by volume is great, then the rate of drug dissolution, which is dx by dt, will be greater. As the concentration of the dissolved drug becomes larger, which is Xd divided by volume, the driving force is reduced. So the relevant question is, how can drug dissolution in the gastrointestinal tract ever be complete? To maximize drug dissolution, the concentration of dissolved drug must be minimized. Of course, this happens when the drug is absorbed through the intestinal wall and into the blood. The rate of absorption is related to the permeability of the drug and intestinal drug concentration, which is XT divided by volume. For passively absorbed drugs, the greater the intestinal concentration, the faster is the rate of absorption. Therefore, dissolved drug concentrations in the intestine can be kept low, which enhances dissolution. When XD divided by volume is no greater than 20% of the CS, this condition is met and is known as sink conditions. Designing a dissolution test. When a dissolution test needs to be designed, several issues or factors need to be taken into consideration regarding the dissolution apparatus that is being used, the dissolution fluid, and also the process of dissolution. A decision should be made regarding the design of the dissolution apparatus, shape and size of the container, the agitation method, nature of the agitation, and the speed of agitation. Regarding the dissolution fluid, it is necessary to make a decision regarding the composition of the dissolution fluid, viscosity, volume, temperature, sink condition or not. The process of dissolution also, a decision should be made regarding the method of introduction of dosage form, which is holding the dosage form in the medium without obstructing the release mechanisms, are relevant to drug testing. Sampling techniques that need to be used. Do we need to change the dissolution fluid? This is extremely important in sustained release dosage forms, for example, or delayed release, in order to obtain a pH gradient or to simulate fed and fasting for a modified release delivery system. Due to the significant difference between the stomach and the intestine, media representative of the gastric and intestinal environments are commonly used. The major differences between gastric and intestinal media are the pH and the presence of bile. Another important consideration is the absence or presence of food in the stomach. When food is absent, conditions between patients do not vary too much because the stomach is acidic, pH which is less than 3 in most patients in the fasted state. The main variables are the type and volume of liquid administered with the dosage form. If water is the administered fluid, the buffer capacity is low, and this would not be a factor in dissolution testing. Although it is known that the surface tension of gastric contents is reduced, the exact physiologic agents that are responsible are not known. Therefore, sodium lauryl sulfate is commonly used in dissolution testing to achieve this effect. The composition of the simulated fasted gastric fluid pH 1.2 is simple, and it will be shown later. In the fed state, the conditions of the stomach are highly dependent on the type and quantity of the meal ingested. Simulated intestinal fluid is described also in the Pharmacopeia as 0.05 molar buffer solution containing potassium dihydrogen phosphate. The pH of this buffer is 6.8 and falls within the range of normal intestinal pH. Pancreatine may also be added if a more biorelevant form of the medium is required. Pancreatine is a mixture of the fat-dissolving enzyme lipase, the protein-degrading enzyme called proteases, and those that break down carbohydrates like amylase. If simulated intestinal fluid does not contain pancreatine, it is indicated using the notation simulated intestinal fluid SP, where SP means sans pancreatine or without pancreatine. Some of the parameters that can profoundly influence the dissolution rate of drug products, such as the buffer capacity, pH, and surfactant concentrations, and how they can be introduced into a biorelevant dissolution test, have been studied. Other considerations are the volume of the contents in the stomach or intestinal segment and the duration of the test, as it related to residence time in the stomach or intestinal segment. This table shows the composition of dissolution media for in vitro dissolution testing, mainly the simulated gastric fluid, and which has the pH of 1.2, and simulated intestinal fluid, which has a pH of 6.8. The composition of simulated gastric fluid is sodium chloride, concentrated hydrochloric acid, and deionized water. It might also contain the pepsin, which is the enzyme pepsin, or also the simulated intestinal fluid. The composition is potassium phosphate, monobasic, sodium hydroxide, deionized water, and also pancreatine might be added. As we mentioned, SGF could be with or without the pepsin, and the simulated intestinal fluid could be with or without pancreatine. There are other commonly used media, including water, hydrochloric acid, buffer solutions, water or buffers with surfactants, also low content alcoholic aqueous solutions. Although water is one of the most listed dissolution media found in a USP monograph, it may not be physiologically relevant due to the lack of buffering capacity. This table shows different examples on how different dissolution media are being used. For example, the dissolution of ampicillin is studied using water as a dissolution medium. Paracetamol is studied using buffer as a dissolution media. Cimetidine is studied using hydrochloric acid as a dissolution media. Piroxicam is studied using simulated gastric fluid. Valproic capsules, the dissolution of valproic caps, is studied using simulated intestinal fluid, and clofibrate is dissolution of clofibrate capsules is studied using surfactant solution. General categories of dissolution apparatus. We have general classification as official methods or non-official methods. The official methods here, most commonly used methods, first appeared in the 13th edition of the US Pharmacopeia in early 1970s. Non-official methods, regulatory guidances recommend 4 dissolution apparatus for modified release dosage form. Although the existing apparatus are adequate for intended purposes, equipments may require either modifications or completely new design. Also, the classification could be according to the technique: beaker method, which will be discussed later, open flow through compartment system, or dialysis concept. The USP has 7 different apparatus that can be used for dissolution testing. USP basket method, method 1, and paddle method, method 2. They are referred to as closed system methods because a fixed volume of the solution medium is used. They provide a steady state stirring motion in a large vessel with 500 to 1000 ml of fluid that is immersed in a temperature, usually body temperature, controlled water bath. The devices are very simple, robust, and easily standardized. These 2 methods are methods of choice for dissolution testing of immediate release oral dosage forms, tablets, and capsules. The use of alternative dissolution methods should only be considered after USP methods 1 and 2 are found to be unsatisfactory. USP apparatuses 3 and 4 are used for modified release dosage forms. Rotating basket apparatus, apparatus 1, This is apparatus 1, rotating basket apparatus. The apparatus is useful for solids, mostly floating, monodisperse tablets and polydisperse drug products. It is basically a closed compartment, beaker type. This is a beaker type apparatus. It is comprising of a cylinder, glass vessel with hemispherical bottom of 1 liter capacity, partially immersed in a water bath. This is a beaker, hemispherical bottom with 1 liter capacity. A cylindrical basket made of number 22 mesh. This is the size of the mesh. This is a cylindrical basket located in the vessel at a distance of 2 centimeters from the bottom. This is a 2 centimeters from the bottom, and rotated by a variable speed motor through a shaft. This is the shaft, and it is rotated, the shaft. All metal parts, basket and the shaft, are made of stainless steel 316, which is inert type of steel. Rotating paddle apparatus type 2. This is apparatus type 2. Like USB apparatus 1, apparatus 2 is useful for solids, mostly floating, monodisperse tablets and polydisperse encapsulated beads drug products. In the apparatus 2, a paddle replaces the basket as the source of agitation. This is a paddle that replaces the basket. Floating dosage forms require sinker that is a small loose wire helix attached to the dosage form that would otherwise float. This could be considered as a disadvantage of the apparatus. If the tablet floats, then there must a sinker is needed in order to avoid floating of the tablet. Moreover, cone formation and positioning of tablet during the test is sometimes hard to maintain. The position and alignment of the paddle are specified in the official books. Common advantages and disadvantages of USB apparatus 1 and 2. The advantages, they are widely spread, accepted apparatus for dissolution tests, apparatus of first choice for solid oral dosage form, standardized, easy to operate, robust, broad experience. The disadvantages or limitations of these of type 1 and type 2 apparatus: limited volume of the solution medium. It's only maximum is 1 liter or 900 ml sometimes. Simulation of the gastrointestinal transit is not possible. It's not easy to switch from one dissolution medium into another. The hydrodynamic conditions are not known. It's not easy to, you cannot determine the thickness of the aqueous diffusion layer, for example, using the apparatus 1 or 2. Dissolution results obtained with USB apparatuses 1 and 2 may be significantly affected by the shaft wobble, location, centering, and coning. These are all disadvantages of the dissolution apparatus 1 and 2. Once again, this is a schematic diagram showing USB apparatus 1 and USB apparatus 2. Once again, this figure shows the instrument or the apparatus type 1 and 2 dissolution apparatus. These are the beakers. They are inside a water bath, temperature controlled water bath. This is the basket, and this is the paddle. If we switch from a basket into a paddle, we switch from type 1 apparatus into type 2 apparatus. USB dissolution apparatus 3. This is a schematic representation of or diagram of the USB apparatus 3. The assembly consists of set of cylinders, flat bottom glass vessels. These are the glass vessels. A set of glass reciprocating cylinders. These are the reciprocating cylinders. Inert fittings and screens. These are the screens. Inert fitting and screens that are made of suitable non-sorbing and non-reactive material and that are designed to fit the tops and bottoms of the reciprocating cylinders, and a motor and drive assembly to reciprocate the cylinders vertically inside the vessels. The vessels are partially immersed in a suitable water bath of any convenient size that permits holding the temperature at 37 Celsius degrees during the test. No part of the assembly, including the environment in which the assembly is placed, contributes significant motion, agitation, or vibration beyond that due to the smooth vertically reciprocating cylinder. A device is used that allows the reciprocating rate to be selected and maintained at the specified dip rate given in the monograph within plus or minus 5%. The design of USP Apparatus 3 is based on the disintegration tester. Operation involves programming the agitation rate in dips per minute of the up and down for the inner tube inside the outer tube. On the upstroke, the bottom mesh in the inner tube moves upward to contact the product, and on the downstroke, the product leaves the mesh and floats freely within the inner tube. Thus, the action produced carries the product being tested through a moving medium. This apparatus is originally used for extended release products, bead type modified release dosage form, particularly beads in capsules. It is also useful for solids which are mostly non-disintegrating. Advantage of USP Apparatus 3, it is programmed for dissolution in various media for various times. The media can be changed easily. It may start at pH 1 and then pH 4.5 and then at pH 6.8. Attempts to mirror GI tract pH changes and transit times. Disadvantages of the USP Apparatus 3: disintegrating dosage forms show too low results. Surfactants cause foaming. Volume of dissolution media is too small. This method is less suitable for precise dissolution testing due to the amount of agitation and vibration involved. This figure shows the reciprocating cylinder USP 3 dissolution apparatus. This is the glass vessel, and this is the glass reciprocating cylinder. USP Apparatus 5 paddle over disc method. In paddle over disc method, the paddle and vessel assembly from Apparatus 2 with the addition of a stainless steel disc assembly designed for holding the transdermal system at the bottom of the vessel. This is similar to Apparatus 2 with the addition of the stainless steel disc assembly. The disc device should not sorb, react with, or interfere with the specimen being tested. The temperature is maintained at 32 Celsius degrees. This is because it is usually for transdermal patches. The disc assembly holds the system flat and is positioned such that the release surface is parallel with the bottom of the paddle blade. The apparatus is used to test transdermal batches. This is USP Apparatus 4, the flow-through cell apparatus. The assembly consists of a reservoir and a pump for the dissolution medium, a flow-through cell, this is a flow-through cell, and a water bath that maintains the dissolution medium at 37 Celsius degrees. The pump forces the dissolution medium upwards through the flow-through cell. This is the upward. Okay. The pump has a delivery range between 240 and 960 ml per hour with standard flow rates of 4, 8 and 16 ml per minute. The flow through cell of transparent and inert material is mounted vertically with a filter system. It is mounted, this is vertical position, with a filter system that prevents escape of undissolved particles from the top of the cell. The bottom cone is usually filled with small glass beads of about 1 millimeter diameter with one bead of about 5 millimeter positioned at the apex to protect the fluid entry tube. These are the glass beads. And a tablet holder is available for positioning of special dosage forms. The cell is immersed in a water bath and the temperature is maintained at 37 Celsius degrees. The dosage form is contained in a small vertical glass column with, as we mentioned, with built-in filter through which a continuous flow of the dissolution medium is circulated upward at a specific rate from an outside reservoir using the peristaltic or centrifugal pump. Turbulent or laminar flow can be achieved by changing the bottom barrier. The medium can be changed to provide a pH gradient, surfactants, and other medium components. Dissolution fluid is collected in a separate reservoir, and the apparatus can be used for dissolution testing of lipid-filled soft gelatin capsules. This figure shows also the USB dissolution apparatus for the flow through cell. USB apparatus 6 and USB apparatus 7. The USB apparatus 6, which called cylinder apparatus, it is a modification of the USB apparatus 1, the basket. It uses the vessel assembly from apparatus 1 except to replace the basket and shaft with a stainless steel cylinder steering element. The apparatus is used to test transdermal patches. Apparatus 7, originally introduced in the USB as a small volume option for small transdermal patches. The reciprocating disc apparatus was later renamed the reciprocating holder apparatus with the adoption of 4 additional holders for transdermal systems, osmotic pumps, and other low-dose delivery systems. The dialysis system. The dialysis system is composed of dialysis membrane. This is the membrane, and is used as a selective barrier between a fresh solvent system compartment. This is a reservoir, and the cell compartment containing the dosage form. It can be used in case of very poorly soluble drugs and dosage form such as ointments, creams, and suspensions. The rotating and static disc methods. The intrinsic dissolution rate is defined as the rate of dissolution of a pure pharmaceutical active ingredient when conditions such as surface area, temperature, agitation or stirring speed, pH, and ionic strength of the dissolution medium are kept constant. Determining this parameter allows the screening of drug candidates and aids in understanding their solution behavior under various biophysiological conditions. The compound is compressed into non-disintegrating disc and mounted so that one surface is exposed to medium. This figure shows the rotating disc apparatus, or wood apparatus called. This is the rotating disc apparatus, and the stationary disc apparatus. In the wood apparatus, the tablet is compressed in a rotating disc die. This is the disc die. The rotating disc is constructed of stainless steel, and the dissolution experiment is performed in a jacketed beaker that is heated by a water bath and to control the temperature. This is the shaft that is rotating with the compressed tablet. In the stationary disc apparatus, the tablet is compressed using a tablet press and then transferred to a holder. This is the holder, and mounted in a water jacketed dissolution apparatus equipped with a motor operating at certain rotation per minute. In this case, the paddle is rotating while the tablet is stationary. In the wood apparatus, the tablet is rotating with the shaft.